Good evening all. We will have the second session which will be handled by Jyoti Electronics, a resource person from Ahmedabad. Topic on reconfigure antenna array simulation analysis and improve performance using optimization in CST. So this is the topic Sir will be handling. Darsh is the application engineer in Jyoti Electronics, Ahmedabad, and he will be handling the session. He did his Master of Science in Physics at Department of Physics, Electronics and Space Science, Gujarat University. He has done project in design a microstrip patch antenna using CST. He is also a certified person. He has won second prize in CMPMS 2023 conference organized by Gujarat Science Academy. So Darsh sir will be handling this session and you will able to see the optimized performance of antenna using CST software. We welcome you, sir. We welcome you for this session.
Good afternoon, everyone. Okay, my name is Darshak Kawar, application engineer from Jyoti Electronics, Ahmedabad. Today in session, we generally analyze the designing and the simulation of the optimization and the antenna array, and some other tool like parameter sweep in the CST Studio Suite. So from the introduction, Jyoti Electronics is a recognition techno trading house based India's companies, which is serving since 2000, 35 years in the hardware and the software domain related to EM and the circuit simulation and the system simulation and the other antenna tools designing and the RF component as well. This is our principle. We generally provide the services related these companies, and our mainly customer are ISRO, SECA, all type of ISRO, DRDO, BARC, HAL, PRL, and other many research institute and IIT NIT engineering college as well. So in today's presentation, we generally saw CST Studio. So CST Studio should have different packages like a Spark 3D, Phase 3D, Antenna Megas, Opera, and WaspNet. So these type of packages is included in the CST software. In designing simulation software, they have their different purposes. We will see like Spark 3D. Spark 3D is generally a tool to analyze the RF breakdown power threshold. Like we can analyze the uh, RF breakdown of the in the corona discharge energies and simulation power of the waveguide structures, and the most importantly hollow structures like waveguides. Phase 3D, as per the name, Phase 3D is a user tooling for the fast analyzing of the complex passive structures, and we also can directly export the result from Phase 3D to CST for analyzing. And this is a analysis for the passive components on the base of the waveguide technologies. Antenna Megas. This is also a tool is included in the CST software. Antenna Megas already have a built-in 350 antenna. You can use directly it in the CST. You can export from Antenna Megas to CST and customize that geometry, so you can get a desired result. So different type of antenna have a in already built-in Antenna Megas. You can just have a input the frequencies and frequency range and radiation pattern range that you want, and it will be automatically generate that type of antenna, and you can export it and export it and open the CST and simulate it. After getting, you get a desired result like S parameter, VSWR, and many more things. Opera is also a tool for the low frequency analysis structures like different type of machineries and we can say electric motor and the other electric mechanical components. WaspNet is a tool for the waveguide and antenna synthesis program for the network. So where we generally build two WaspNet two waveguide component, and we break it down in the simple 2 to 3 terms, and we just analyze the separate by separate terms. So WaspNet is used for the extraordinary explanation about the waveguide tubes, and we can see hollow type structures and TWT like that structures. Abacus is the mechanical software related domain. So we can analyze some different mechanical thing like stress and materials geometry and the non-linear parts of the materials, and we can say about the machineries. You can see the toughness and the how the temperature analysis will be the analyzed by Abacus software. So MCAD is also software in the CST. Further with the CST, it's also provided by the Dassault system. So all this software I provide under comes under the Dassault system. So MCAD software is the generally have a different type of tools like IVCAD, IQ Star Vision. All have the power amplifier analysis related to design and simulation. So this is generally helpful for the machinery things. You can there is software providing plus the mechanical some things are there machineries, and you can analyze the RF power amplifier as well. So today's session, CST mainly focus on the CST Studio Suite software. So we can say the CST Studio Suite 2025 have a different features, and we will see it, what is the included related to antenna and the other component we want to design and the simulation part of that component. How CST is can be useful to for that. Certain circular antenna array antenna for reflector antenna and different type of antenna, we can say the all type of antenna we can design and simulate it in CST. So CLC tool is for as per the, we can say CST is using in the designing of the RF component and the like antenna and the other things like filters and the waveguide couplers and the uh, many other RF component you can using designing simulation. So for that we can say this is a useful software that is big used in the different domain like aerospace and the defense and communication and automobile. Every sector they have their own categories by CST software. So CST software that generally provide a different solver analysis. So for the different purposes, we using different solvers. Here is the base view of the different servers like CST Cable Studio for the cable harnessing and cable analysis, and signal integrity, power integrity analysis. CST PCB videos, EMI EMC analysis for we can use the PCB Studio solver in CST. CST Microwave Studio and CST Design Studio is generally we can synthesize the do different structures and combine it, and for a hybrid analysis we can use the Design Studio. CST Particle Studio we can analyze for the particle like structure like electron and the electrogun analysis. So we can also design and simulate like that per particle. CSTM Physics Studio is generally for the thermal analysis and mechanical analysis. CSTEM Studio is generally for the time domain, frequency domain solvers and using the different type of antenna and the filter type of technology designing simulation. So in coordinator, we can say CST Microwave Studio is a specialized tool for the fast and accurate 3D electromagnetic simulation and high frequency problems. Like you can see, we can different type of antennas, horn antenna, helical antenna, array antenna, and the coaxial, rectangular waveguide, TWT, and the filter and resonator and all type of RF component we can design and simulate it using the Electric Microwave Studio. EM Studio is generally used for the um, analysis like a structure of the low frequency structures. You can actually can design in the simulation like actuator breaker and the generator motors and sensors. So EM Studio is useful for that. CST Particle Studio is also a tool for the analysis of the particle like structure like electrons and the different of particles, proton and neutron. So for that we can say we can design electrogun, magnetron, TWT and the multi-beam gun. So particle like structure we analyze CST Particle Studio. CSTM Physics Studio is tool to analyze the thermal and mechanical structure for a particular temperature. What is the structure or RF component or a circuit breaker or any component? It how behave it's particularly that temperature. We can analyze the thermal analysis for that thing. So we can use the M Physics Studio for that. CST Design Studio. CST Design Studio is for the complex structure analysis. So if there is a different part of structures like microstrip and some other part are there, so we can decompose that and simulate it separately one by one part, and after that we can merge that the result, and we can use for the hybrid cell simulation analysis. So CST Design Studio is for using for that usually. CST PCB Studio, we can generally analyze the CST PCB solver, this studio, for the EMI and EMC analysis, electromagnetic interference and electromagnetic compatibility of the PCB Studio. So you can check it out how the where is the temperature analysis and the EMI analysis we can perform in the PCBs. Same goes for the CST cable studio. In the cable studio, we are just generally analyzing different type of cables like two wire cables and the coaxial cable. So for that, we can analyze signal integrity, power integrity, EMI, EMC analysis in the cables. So different type of cable analysis we can use in the cable studio solver. So this is useful for different purposes. Also, there is a general software that we use in general purposes like antennas. So we can say transient solver or T solver. So T solver in CST we can generally use for the electrically medium and the large structure for the broadband analysis. If our antenna, for example, our antenna has a we are designing and simulating. So you can say if the broadband are there, so frequency range is gigahertz. They cover most of the gigahertz range, and they have a broadband antenna. So you is go with the tree solver. If there is a particularly 5 gigahertz, for example, 5 gigahertz, so some frequency you can go with the frequency domain solver. So as per the frequency domain solver, narrow band and the single frequencies, the electric is small and a medium size problem, and the periodic structure as well as broken port analysis like metamaterial and other things. So and there's some special solver are as well there, eigenmole solver. So eigenmole solver strongly connected for the closed structure like cavities, and the other structure like electrical large structure as well. Integral equation solver we can use for the electrically large server and dominate by metal things. And the asymptotic solver using for the radar cross section analysis RCS, they generally use the shooting and bouncing ray method. So for the radar cross section analysis, if you have a radar analysis in the your component, so you can use asymptotic solver. Generally it's analysis of metal things and very large object, electrically large object. And the multi-layer solver for the layer by layer structure analysis. So if you have multiple grounds and the substrate and pitch and the multiple analysis you have to run. So in layer by layer structure, you can use a multi-layer solver. So CST Studio have some different solver for the different purposes. You can include it, and also you can have to measure some things. So electrically size of the structure, it's also important because from that we choose the solver and we choose the that method that can be used for the simulation of the structure. Material types also have a different type of material library in CST. You can use it, and also if there is a new material, you can there is option a new after no material updated. So you can just simply add the permittivity and the permeability, and you can generate a we will see it you can generate a new material, resonant behavior and typing of meshing. So different type of meshing are there, and some method are there to accurate analysis. So meshing type of are there like hexahedral, tetrahedral and surface meshing for different purposes like T solver. Broadband analysis we generally use the hexahedral meshes. For the single frequency and the eigenmole solver analysis, we use the tetrahedral surface, and the integral equation solver, we generally use the surface meshing solvers. In the CST, there is option you can choose the different type of meshing, and also you can decrease or increase the meshing as per the requirement. If the large amount of meshing, it will give the best and accurate result, and but it take more time and more resources. So different meshes are there, and adaptive meshing also option are there. Also CST has a help tool are there. If you doing designing, you need any type of help, so you can generate a in using the CST. If you didn't get a between idea, so you can use the help tool in CST section. We'll say this is a basic window of the CST. So when you open the CST, also you can have a component library are there. So component library already built in some antenna filters and couplers are there. So you can directly review that and use it for your designing and learning purposes as well. Here you can see, for example, I search the antenna and different type of antennas are there. So I can directly use it and open it in CSTs. So EST simulation workflow are there. So if I want to design something RF component, and so I get an idea, I will just designing it and simulating it. And also get if I don't get a desired result, so there is some option out there. You can just optimize it using optimization option and in CST, Also, there is a parameter sweep option are there, so you can analyze the result from the different range of the some geometries range, or you can see the electrical range, a different type of that. After that, you will finalize your product, and the final is go for the synthesize. So there is some workflow are there, so you can just follow and get a desired components with better result. This is the project template. When you open the new project and in CST, so there is some microwave studios and optical are there for the antenna. Say the other particle studio and the low frequency component EMI EMC analysis. There is a different option are there. This is a preliminary window that we can use for the designing of the CST. You can see the left hand bar, navigation tree are there, and preliminary window for the designing, and the above one is the raving bar project messages. If the during the message, if any error or any messages are there, you can see the project messages. Parameter list, you can denote the parameter using during the designing, for example length, width, and the height of the structure. If you define any variable, you can go with the parameter list. And process window, you can also during so the designing. For the designing purposes, CST also have a different shapes are there, like cone, cylindrical, sphere, bricks, and the ellipse, and the different type of other shapes are there. If you want to design some random design, there is also option are there. So we will see it in next. One second. Okay, yeah, you can see my screen now. Primitives.
Yes, sir. Yes.
Okay. So next, our view option are there. So also there is a view option and hide option are there. If you have a complex structure, like you have a box, and inside some other structure are there, so there is an option like a view option. You can hide the above option, and you can see the inside option. Also there is a cutting plane of the, if you want to see the what is the inside the structure, you can just cutting plane option are there. So you can simply view the different type of view option. So here show and hide option are there as well. Also there is a peak operation are there. So if I want to present some operation, so particularly at some faces and some edges, so there is a peak operation are there. So firstly you can see here the peak operation at the edge, at the point, and here you can say edge, or here you can say surfaces. I just generally pick that surfaces, so can our next operation will be performed there if I use that peak operation in particular way. So for other things are also there. You can change your coordinate axis from the global coordinate axis X Y Z to W C Z. So if you want to change your coordinate system, for example, here is the bricks are there, and I change the coordinate axis to new coordinate axis WUV. So from here, there if I further designing, they will count from the here to 0, 0, 0, 0 for that point. Also, you can change the coordinate axis as edges and surfaces as well.
Yes, sir.
Here I already as I explained, peak operation are there, so you can pick the edges, point, and surfaces. So for further operation, you can denote here. You can operation, if you want to denote some operation from particularly some faces, so you can use the peak operation. Also you can change the coordinate axis from the global coordinate axis XYZ to particularly some different axis WUV, as you can see in the figure. So after that, that will be calculating the length and the width and the some coordinate from their axis, not the global coordinate axis XYZ. After denoting the some working coordinate system, you can also change it and rotate it and transport from one point to another point as using transport operation and rotate operation. Also, there is option are there. So new coordinate system for the new designing. You can change also some perform the boolean operation. So if you have a two projects and two files are there, some bricks and for example the bricks and the sphere are there, you can add substrate extreme and the trim you can performance the operation as per the, your requirement. So for the random operation, you can perform this curve modeling tool. Here you can see if I want to design some arbitrary designing, so I can select the some points and denote some ranges like XYZ values of the some point, and you can just design accordingly that you can fill with the material as well. So for example, I just design some uh, shape like this one, and I want to fill material with PEC and any other material, I can also fill that using this curve modeling tool. Also during the designing, so there is a blend and charm edges operation are there. So if you want breaks, if I want to smooth the surface, you can use the blend and char operation in your designing. During the designing, if I have two parts and the one part is will be want to rotate or scale or transform, so you can use the transform operation. So generally we can transform the from one point to another point, and other will be the at the same point as they designing. Here is the cell operation are there. If there is a solid bricks are there, you can see here in the this shape. So we generally using the pick operation, pick this face and the two faces. See that you want to shell operation and select the cell solid and thicken sheet. You can see the this structure will be hollow after this performing this operation. So for the designing purposes, the different operation are there. Also, please ask any question during the presentation if you have, or if you have not, you can just simply stop me and ask anything.
I have a question that using CST, how can we
Mm.
add those pin diodes or vector diodes for the purpose of reconfigurable antenna? It is expensive.
Sorry,
And the procedure what we follow for the addition purpose of the diodes, how it will be decided these
I
steps?
I think your voice is crumbling. I didn't understand particularly. Can you just type your question, please?
I
Ma'am,
can
Lakshmi ma'am.
am I audible?
Ma'am, can you type your question in the chat box?
Yes, please. Here we generally analyze the antenna array because you will see it. Can I go further? Can we go further or wait?
Sir, you can continue.
Okay.
Okay, thank you,
So
sir.
next operation is loft operation. So here we can simply select the two faces, and after that you can join with some any material and any range of the theta. Also you can change the smoothness of the surfaces low to high as per the your requirement. Here you can see I have a cylinder and I have a bricks before I using the loft operation, and I you can see the whole horn type structure I just designed, and also you can change the smoothness of this structure. Also there is a bending operation are there. So if there is a solid structure are there and the thickened sheet are there, so you can generally bend using the bending operation. You can bend the above structure on any other structures. Also bending the structure of the seat as well. So if you have a sheet of the some component and you can bend on upon a different structure, so you can also use the thicken sheet and the bending operation as well. After the design completing, we are here is the for the input powers and the input signals. So here is a different type of ports are there, district port and the waveguide port. So here is a two type of port are there, so like district port, also you can say lump element, you can see the RLC value, and the waveguide port for the analysis of the all structures inputs. From example, here a district edge, a district port, we generally select the 2 point or any 1 point on one surfaces, 1 point or one edges. It's look like this one district port, and you can generally create it using simulation tools. District port same goes for the waveguide. Also, you can go with the district port using this wells and waveguide. Select the 3 point or one second.
So Windows screen is overlapping with
Yeah, yeah.
presentation.
I don't know why this is. So in port definition, so you can generate a waveguide port as using the two edges or 3 point or any surfaces. You can using the peak operation select the some surfaces or edges and a waveguide port. So waveguide port you can generate using this operation. Also there is a for the generating of waveguide port, we have a different options are there. For microchip edge antenna, that will be automatically calculate the port size and the coefficient of the district coefficient as well. So you can see here, for example, I have designed a microchip patch antenna. So here is the ground plane, here is substrate, and the above one is the patch. So as per the our requirement, we generally design a port automatically using the macros operation are there in the CST. So it will be automatically count length and the width and the size of the waveguide port. Otherwise, we have to input manually here. If we directly don't count the waveguide port, so I have to input manually size of the waveguide port. But in here case, you can also generate it. So after designing, we go with the simulation part, and after simulation completing, the result are there. So 1D, 2D, and 3D result are there. So for the 1D result, we can analyze the S parameter, balance, energy, and the port signal as well. For the 2D analysis and some other analysis, electric field, magnetic field, and the voltage current, the surface current as well. You can analysis on the for the 3D analysis. You can say the radiation pattern, far field pattern, so different type of analysis are there and different type of result are you can analysis after antenna designing or any other component designing. For example, here you can and also analyze extra ratio of the CST part like in 1D analysis, 1D result analysis. Also you can analysis is impedance matching. If you have a give the 50 ohm input impedance, you can also show the output. Hello. Also can analyze the output impedance, and also you can analyze the VSWR ratio, voltage standing wave ratio, and the S parameter. S parameter will generally denote the in which frequency. For example, here is the 8.26 gigahertz frequency our antenna is resonating or it transmitting or receiving it for that frequency range 8.2 gigahertz. So S parameter, VSWR, and some other parameters are there. Also you can analyze the electric field and the surface current as well. So also there is a animation option
Excuse me,
are
sir.
there. Okay.
Sir, in that switch chart, how to observe the plot, sir?
Okay. here particularly 0 point are there. So here you can see any point in CST there is a point operation are there. You can generally double click here and the point the 1 point. Here you can see here you can see for 8.2 gig to 6 gigahertz for that frequency range we can see here 60.83 ohm for our this ratio. So I for example I just give the 50 ohm input and here is the impedance matching for the 60 ohm. So it's slightly mismatch but you can see here a value. Also if you want to see particularly in this curve range, one second. You can just move this cursor and you can also see the where is the 50 ohm are there for which frequency range. You firstly select the frequency from the S parameter and you can see the 8.26 our antenna is resonating, and for that frequency you can analyze here how the impedance is here is a 60 ohm is slightly mismatch. You can optimize the design and the design geometry. So after that you can analyze the our results. Okay, it's fine. Or any other question about that?
Sir, the 0 point I couldn't understand, sir. This one, okay, sir. The value is 60 ohm.
Uh-huh.
You mentioned about the center point now, sir. How to observe, sir?
This is the center point. This is
Yes,
if
sir.
you can see here.
Yes, sir.
See
But
0.26. Here one value are there. For particularly that value, we can say the our impedance is matching particular performance at that frequency. You can only follow this red curve. You can't select after other any point around the red point, red line. So you can see here red line is going from here. So if you select here, when your cursor goes to here and the 1 point is here, so you can see the our frequency is changed for 8.2 gigahertz is also changed, and impedance matching is also changed. So maybe the here 8.26 gigahertz are there, maybe the 7 gigahertz frequency it's 50 ohm, it's completely matched from here.
okay, okay,
So
sir.
that is not useful because our antenna is resonating in 8.26 gigahertz. So impedance matching particularly for that frequency is important. So here we have 250 ohm of the output. So we have to match the in output impedance as we input the 50 ohm. If you want to change the input impedance, you can also change it.
Okay,
It's
sir.
fine.
Okay, sir. Yes, sir.
It
Thank
will be more visible when we can see in CST. So you can just practice it after how to rotate and how to see these values. Okay, and in 2D and 3D result, electric field and magnetic field and the surface current is are there. You can see here the red part is showing this highest value and blue part is lowest. Also, their animation option are there, so you can see how the electric field generate and where in which point electric field will generate and going in which direction. So animation option are also there, surface current is are also there. Also you can change the far field, see the far field and the gain result are as well. So in far field result here is a 1 day result are there. So in which direction it will be showing the our this is the rectangular part is the our antenna for example, and this is how they are resonating. For this is the part, this is our antenna and this is our radiation pattern, far field pattern we can say in which direction they are resonating. Also you can see the gain and the directivity of the antenna. This is a post processing step. After that we can see the parameter sweep and optimization of antenna. So designing part of the antenna or any other component of RF component is completed. You can also see the result, but if result is not okay with you and you want to change some result like impedance matching, VSWR, S parameter, radiation pattern, gain, any other result you want to change, you have to study it. In which geometry, which part of the component is reason is the reason for that things, and you can change accordingly your requirement. Parameter sweep is also one of the part of the optimization. So here you can see parameter sweep. For example, I have a one antenna and antenna for example microchip edge antenna. So you can perform in any antenna, horn antenna, any filters, any couplers, any DWT waveguide method are the same. but here I just show the tricks how to, you can do the parameter save overview. You can, if you want to length, change the length and show the values. So for a microchip edge antenna, and if I want to change the length of the patch, radiating patch, so and I want to see what is the result will be changed, so you can see the parameters view, you parameter sweep operation, you can use that. So here we generally denote them some range. For example, L for the length operation, I just denote the L, give the value of the linear shift from 21 to I want to go with a 30. So that will be automatically change the length of the our substrate or any selected part that you select of the patch, or 21 to 30, 21 to 40, any values that you given and sample that you want. So for that frequency range, it will be count the every frequency. If you select here 10 sample, so 21 to 30 in because frequency of 1 gigahertz, they will count the our S parameter. You can show how it will be changed for that.
So can we
So
take this as a pre-processing result, sir?
yeah, after the designing, post proceeding, this is post proceeding the operation at that.
Okay.
If you can for example here only just take a two values, so you can see the how our s parameter is changing. It means in which frequency our antenna or any other component is radiating. So if there is a multiple parameters sweep are there, you can see the how our s parameter will change by differentiating the and using the different length. Optimization are also there. If you have some setup file for the optimization, and you want to some have a goal in your mind, so you can also set the goal function as well. So for that you can use the optimization in the solver as well as optimization in simulation option are there. After select open the optimization option, and for optimization how it's work, I generally show here. So if I for previously I just designed and I got this result S111, but its result is not good. So I want to go decrease my result because in S parameter or in antennas, generally below minus 10 dB is the acceptable for the that frequency range antenna is radiating or antenna is receiving for the that frequency range, because and our result must be below minus 10 dB. Here is a minus 10 dB, this is above minus 10 dB, so I don't want that result. So I want to change this result using optimization. You can optimize the result, how it works. For example, here is the point, some point are there, hollow structure are there, so I want to change this point, and x and y is the length of this length and width of this from this side of the structures. So you can generally give the operation, change the length and width such that I get a result from below minus 10 dB. My structure will get the result of the S parameter, not only S parameter, but any type of result, VSWR and the impedance. Structure automatically change that value and see the which value is nearest to your goal function. For example, I give the nearest to 40. I want to nearest to minus 40 dB result, but it will gives the 35 maximum. That is the only possible things. So that will be automatically change the this structure length, width, and that you enter, and it will give us the expected result, nearest expected result. So here example are there, x1 and the y1 is the distance between this hollow structure to this wall and this wall. Values are 4. So I take a minimum and maximum values for the global coordinate axis minus 10 to 10. I just give the range, use the all the value between the minus 10 and 10, and also for the y1 minus 10 and 10. So try and all the values and give me the expected result. So after the goal function setting, you can see the our s parameter will change. If possible, they will give the nearest value the our s per our desired results. So here you can set the goal function after in optimization option. Here you can say select the target less than equal to, greater than equal to. For example, I want to result below minus 20 dB. So I select the less than equal to minus 10 dB, and the previously here you can select the which component you have to change, and for that after that you can select the goal function and you can optimize it. After that optimizes, you can see our result will be there, how it will be performed after optimization. You can also compare that. CST also have some denoting option are there. So if you can just generate this structure, you want to measure this length. Also, there is a option out there. You can measure the all the component sizes. Also, S parameter after simulation, you already get the S parameter and VSWR values in time domain and frequency domain solver. Also, we can go with the array function as well. So for the multiple analysis array function of the high gain and the high directivity, some array function are there in CST function. So array function is generally use the multiple antenna as the same ground and the same substrate. So, for example, I take a microchip edge antenna. I design one antenna and use it multiple times in matrix forms. So I can use the array function as well. So it's generally for you can use for the high gain and the high directivity in particular range. So you can see here I can just design a one microchip edge antenna or microchip structure, and if I want to go with the array like 4 by 4 array, 8 by 8 array, so array option are there. So you can use directly array operation in CST. CST will directly provide some uh, array things that we can directly generate and input the operation. So you directly will get the results. For example, this is a microchip antenna for single port, single direction, and the radiation pattern are there. So after that, you can select the simulation project array task. Here you can select the 8 by elements in which size you want to generate. For example, 2 by 2, 4 by 2, or 8 by 8. You can select. Also, you can select the shape as well. If you want to orthogonal shape or rectangular shape, and the other shapes are there. Also, you can select the spacing between two element or one element and the second element. You can select the also spacing, which you have to if you input the space between that. Also you can have a set the active and passive element as well. If you design an array and if you want to not actively all the element, some part of the your component you want to active and some part of the component you don't want to active, so also there is active and passive operation are there. Also some excitation are there. If the Taylor excitation are there, for example Taylor excitement and Chebyshev excitement are there. So in Taylor excitation, so they are not exciting with the same power. So you can see in the figure as per the figure, as the red one, it's with the give with the high power, high amplitude, and the other one decreasing yellow, green, and the blue ones. So that means in array function, this is a small square is the one antenna, or for example one antenna or any other component. You can perform. You can see the multiple array are there, 8 by 8 or 60 by 60, and we will give the different input power or input amplitude to all component. You can use the Taylor excitation. If you use the uniform excitation, that will give the same power to the all component. Also, there is a option of the unit cell operation are there on the boundary condition. If you want to perform on the unit cell, there is also option are there. So well, in boundary condition, you can select the unit cell and the also can electric and magnetic boundaries PEC, perfect electric conductor boundary condition are there. So different boundary condition and the Flocon mount and the FSSR different structuring and designing are there in CST. You can see a microchip patch antenna array. So here is the unit cell design. You can see how unit cell boundary condition affect the our results. For example, here we take the 4 by 4 array Taylor excitation. You can see here and 4 by 4 all antenna middle one is the red one, so they will give the same power, but this will be not the give the same power. You can also select in group. So Taylor excitation it will be not divided the uh, same power, but you can see here radiation pattern. What is the change between that? In the Taylor excitation, radiation is like this one, and if you see here, main lobe of this magnitude is 15.07 dBA. So after the uniform excitation, you can see here, this is the same 4 by 4 array, but uniform excitation. That means we give the power of the old antenna same. And here you can see our main lobe is slightly increasing, 70.4 dBi. So but you can also see the side lobe is increasing as well. So in particularly direction, if you want to increase your gain and in particular direction directivity, so you can use the Taylor and the uniform excitation, and some other excitation are also there in array function, so you can analyze as well. Here you take the same example for the 12 by 12 array excitation. uh, Whenever they increase the number of the antennas and the number of the patterns, that will be give the high directivity and gain. You generally use for the satellite communication and the outer space communication. It's you generally use the massive array systems. This type of antennas is using in ISRO massively for the satellite communication as well. So also there is a Taylor excitation of 12 by 12 array. You can see here frequency of that our antenna and in which lobe direction. You can see here 25 dBi, and in particularly direction. Also, it's a 12 by 12 array in the uniform excitation. You can also see here main lobe magnitude is 26. It will be increasing, but also side lobe is increasing as well. 16 by 16 array, same. Also, you can optimize the option in the array as well. So for same for the antenna array optimization, you can in CST perform the optimization. You can see the radiation pattern and the some VSWR as parameters values, and you want to select the spacing between the antenna and the geometry of the changing antenna, and it will give the desired results. So antenna or array optimization are there. Also, there is a feeding network is also important. As we previously said, there is a different type of feeding network are there, but here we take a waveguide port feeding network in different ways. There is a district port and waveguide ports are there. So feeding network is also important for the beam steering and the beam abilities. If we will see it in MIMO antenna, and the series feeding and the parallel feeding of the antenna is also important. So see here series fed microchip patch antenna. So all antenna are fed with the one waveguide port, and you can see is the series one, and this is using a coaxial one. Coaxial feeding networks. That means we can see the series and the parallel network as well. S parameter of the series and the center one, and S parameter is the end fed. Though these are the different methods using for the your particularly desired results. Use any method to get your result in array function. You can trial and error method we generally use here. So here is the far field patterns are there. So in particularly which direction you want to radiate it. So also is useful for the far field analysis. Here you can see the animation of the electric field and the magnetic field as well. And here is the electric field of the series and the series network of center field. Center field is generally used the coaxial feeding network, and the series is generally used for the waveguide port. Both are using waveguide port, but one is the like a ground plane, substrate, and patch, and another one is the coaxial feeding. As you can see, the radiation pattern is and electric field is slightly changing, and how it is varying with the time is also changing. Oh, so here is the parallel fed microchip edge antenna. Also, you can see here all antenna is connected with the one strip, and after that is will go with the uh, waveguide port. Also, we go with the coaxial feeding as well. As parameter, you can see here is slightly changed, but in some geometry, it will be changed a lot. Here you can see red one is coaxial and green one is the microstrip. Also, you can see how the radiation pattern and the our S parameter that denote that our antenna resonate in which frequencies, that will also change. Here you can say the parallel network electric field. Also you can see the how the radiation pattern is will be changed. Here is the side lobe is decreasing compared to first one, and you can see the higher directivity as well. Here is a huge parallel feeding microchip patch antenna, so you can uh, perform the different array task in particularly give the same, we can same input. So we can here we do not give the output of the all of this, generally connect the all of these, and only one waveguide port are connecting from this strip line. That will the power all the patches, not the separate patches. In in previous array antenna, we provide the power of the separate antenna. In each antenna page, in antenna ground plane, we provide the power of the separate thing using waveguide port. So here only one waveguide port are there that is providing the power of the all of the things. Here S parameter, you can see the electric field as well, how it will be resonating and how it will be varying with the time. Also, you can see the how the radiation pattern will be changed. MIMO antenna technology are also there. So this is the same like array antenna, but it's little bit different. We can see here in transmitting and receiving antenna, we if you use all omnidirection in the array antenna, we can say that in particularly one direction that is radiating, and we can say that is resonating in particularly one direction with high gain. But if I want to cover the all the things like omnidirection antenna, that will be cover the 360-degree over in of antenna, you can generally use the MIMO antenna. So MIMO antenna is generally concept similar like a antenna array, but you can say our feeding network of the patch antenna or our radiating patch is the rotating with 90-degree or 180-degree. So that will be cover the all the direction, and you can see the all the direction that will cover, and we can achieve the our omnidirection or radiation pattern that will 360-degree. We will see it firstly. Also, MIMO antenna is using for the directivity, beamforming, and beam steering for the particularly some results. We will see it. Here is the example of the MIMO antenna technology. A few terminology about the 5G MIMO technology, massive MIMO, beamforming, and beam steering are there. So, for example, few assumption are for the MIMO antenna. You can see here, here is a single radiating patch, radiating element, or a single radiating antenna are there. Its radiating pattern is look like this one. So now I increase the two radiating patch and the two antenna in series. We can say a 1/2 array antenna. So you can see the directivity will and the gain will be increasing in particularly one direction. If you can see the four antenna, you can see the directivity and the gain in increasing in some particularly one direction, but it cover the less of the direction, not 360 direction. Here you can see almost 180-degree cover, but here not. So gain will be increasing, but it's not cover the high most of the range during the about the antenna. Also, there is a beam steering and beam forming operation are there. You can change the amplitude and the phase of the antenna arrays part separately, so that you can change the direction of the beam direction of the radiation of the antenna. You can see here it's radiating above part of the antenna, but you can see here the direction will be changed in left hand side. Also, you can change the amplitude and the phase. You can derive the in right hand side. In both side you can change the direction. So it's you generally used for the some directivity. In particularly some direction, you can use the MIMO antenna and the phased array antenna as well. So here
Sir,
is
a small doubt, sir.
okay.
Sir, actually, there are two options now, sir. Realized gain and total gain. Which should be considered, sir, to calculate the gain?
Where in previous
Yes, no, sir. Even in array also, we have to calculate the gain, no, sir.
uh,
There are two gains available in CST. So, realized gain or total gain, which gain we should consider, sir?
for the total gain we are calculating real and imaginary part, and for the real part we generally okay, what's the we can say of the real component, but we for the practical analysis we take a total gain in real life practical analysis.
Okay, sir.
Here is the 5G MIMO antenna in beam forming, so you can see the in which particular direction it will be connecting, and give the high directivity with high gain. You can see the our antenna is below minus 10 dB. Two frequency are there. One is 3.3, second is 6.3. So our antenna or our prototype is resonating with the two frequencies. Also you can see here MIMO antenna. It's mostly part are the red one. So you can say the omnidirection perfectly MIMO antenna. So that will be cover the all the direction above left hand side. So that will give the good output coverage. Also you can see with the MIMO antenna, LTE MIMO antenna. So some assumption are there for for this type of antenna. We have to some particularly geometries are there. In the you use the circular patch and the half of the ground. You can see the um, uh, ground plate that is cutting at the port is introduction in the ground plane. So different method are there using in MIMO antenna after the designing. So for the improving result and the improving the directivity of the antennas and the MIMO antennas especially. Here you can say S11, S22, S3, S44. So S11 and S22 generally denote the first antenna output results, and the second ports are there. If we have different ports are there, so F22 for the second, F233, and F44 for the fourth port antenna. So here we take a four component, four patch, and give the separate waveguide port for the each antenna, and it will be generating a that radiation pattern. So it will give the S11. S12 is also are there. So it will be the denote like the S12 is denoting for the one antenna, first antenna to second antennas, first antenna to second antenna not interfere that results in that radiation pattern. It must be below minus 20 dB is a good isolation for the MIMO antenna. If you're designing something like that, so minus 20 dB. You can also see the F2, 3, and the 3, 4. All four antenna, 16 results are there. So different results. So you can say the good isolation is needed for the MIMO antenna as well. That means one antenna's radiation pattern which not interrupt to other antenna nearest antenna. So isolation is also must be good. Here you can see the our firstly two antenna in um, below side. So about two antenna is 180-degree phase different. Also you can manage if there is a square box are there, square MIMO antenna are there. You can see the 90-degree phase difference. So that will cover the all the part of the antennas. So you can see the 360 or omnidirection antenna you can design. Here is concept of the multi-coupling and the MIMO antenna, LTE antenna. So for the high gain and the high output, you can design different type of MIMO antenna. Here is a waveguide port 1, 2, and 3, 4. So you can perform the different inputs power are there using waveguide port and generate some good result. So this is our presentation about the optimization and the antennas, basic antenna. Do you have a particular topic you want to cover, and do you have any question related our presentation? You can ask. Also, if you have different queries, you can mail us on this email, so we can review that and solution provide the solution about that.
So there are few queries in the chat box.
Okay.
Shall I read it? From Rakim onwards. Yeah, Rakim. Yes.
Okay, one by one taking we can queries. The recoverable antenna also I'm designing are for the CST, but we don't go with the detailed ones. I directly go with the how to add a diode in our CST, and I take a directly example. Can you see my screen?
Rakiman? Yeah, she is available. Yes.
Okay, you can see my CST screen now.
Yes, sir. Yes.
Okay. Here I just take some rectangular microchip edge antenna array, for example. But if you want to reconfigure antenna, you can design it this way. I can also share their workflow for how to design. But here I directly go with the how to deploy the that diode things. For example, I want to deploy a diode from here. One second. Between two these pages. So I select the this edges point between page. Here is peak operation are there. Different peak operation are there. So you can directly use the peak edge or peak edge center as well. Here I say select the peak edge center. So using these peak edge and double click on here, you can see the here is the point that already peaked center of this line. Same goes for the other one. And here is the simulation way. You can see the lumped component are there. Here you can select the diode and apply the values of different R and C, GS and IB, and you can after applying the your appropriate value as per your requirement, you would just click on OK. Here you can see after for the between two pages, you can see the our diode is will be created. For other lump component also you can deploy it. RLC series and some parallel and the short circuit diode are also there. Short circuit are there, and also you can apply to some touchstone as well. So this is I take for the example any 2 point. You can deploy the diode anywhere in your prototype using the any 2 point, any two edges or any surfaces as well.
But what about the choke and DC block capacitor, sir, for the diode connection?
Where Flocon?
We
Where
want to
you?
give biasing, no, sir, for the diode.
Sorry.
Do
Okay.
that, sir.
What sir?
For any kind of reconfiguration for diode connection, we have to apply the biasing, no, sir,
Mm-hmm.
like DC choke and DC blocking capacitor.
Okay.
For one diode, how to give that those things, sir?
There is also option in schematic way. We can see in further. Also, some option are in, for example, in schematic way. If this is our prototype, some option are there, but it's not available in this version. I will set the workflow how to do that, particularly in diode that thing. It's okay with that. You can email us just on that number or that email, so I can provide a detailed overflow for the that DC things analysis in the diode in reconfigurable antenna, because right now it's not showing in this version, so I can take it separately. Polarization you can see in the radiation pattern, and also you can see the cross polar and the copolar of the radiation pattern of the 2D graph. You can see in the far field analysis. If I can say, I took a second example. Check time. for that. For vector modeling, I give the present one PDF file with me. I will share that for the vector modeling.
Sir, can you share it in the chat box?
No, we can I directly can't share with that because it's in share folder and we have to firstly give the permission from the above. So take a permission from the above.
So you can share it with me. I'll share it in the group.
Okay, sure.
Oh, thank you, sir.
In far field result, you can also check axial ratio as well. We will see it. One second. How to check the orthogonal polarization? You can see the E theta in E phi and the cross polar and the copolar in analysis in far field analysis. We will see it. Okay, we will share the workflow as per your requirement. Mostly it's radiating element are there. I will show the axial ratio and the radiation pattern of the far field analysis, also orthogonal and the cross polar and the coplanar. Any other question from your side after completing the simulation? I will show that things. If you have any other question, you can ask. Also, I
Sir,
will.
how to take the front to back ratio, sir? FBR
Sorry.
back ratio.
Okay.
Sir, one more doubt, sir.
Okay. Say.
Hello, sir.
Yes, sir.
Sir, can you show the demo of Champer, sir? I couldn't be able to do the Champer at sometimes.
Temper.
Is it possible, sir?
What things? I can't understand. What you want to do?
Champer option, sir. Champer, which you have shown in the PPT. Champer.
You mean uh, with sample? You means parameter sweep or something else? Where where you shown the PPT in middle of the PPT? I can't understand. What? Hello.
Yes, sir. How to do the Champer option, sir?
You mean change the excitation? Hello. In array task? Hello.
Can you hear me, sir?
In array task, you want in array task, na? You want some operation in array task, temper operation. What you mean that?
Yes, sir.
This one?
No, no, sir. In normal single and yes, sir. This one, sir. The corner champering, like that.
You mean shape of the array antenna or any lattice spacing between that antenna array? Here, what do you want to know? Hello.
Yes, sir. Yes,
You
sir. I got it, sir. We have to select the shape, right, sir?
right.
Okay, sir.
Okay. This simulation may be done. Any other question? Otherwise, I can go with the that final thing.
Any other queries?
Hello.
Yes, sir.
Oh, we will see it. 1 second. I will share the screen and with the result.
Okay, okay, sir.
Any other question? If you can ask, you can show the result directly.
Sir,
Hmm?
sir, can you hear me, sir?
Yeah, I can hear you.
Sir, is there any possibility to do the certifications in CST, sir? Is there any resources to get the complete idea, sir?
What do you want to do in CST? Do the sorry.
Certifications, sir, CST certifications. How to
Oh,
get certificate or how
CST.
to get all the things in a single resource? Is there any resources, sir, available, sir?
Particularly not, but CST have a help tool are there. So in search bar option, 1 second I will show you. Search bar option there is a help tool are there. So of the all operation on the all simulation part and of the all solvers, how to you can get a idea. You can using the CST help operation. Also you can visit the website of the Desert system. So there you can also get some idea about website.
Okay, okay, sir. So we can also learn through the Dassault Simulia. That's also that is also same,
Yes.
right, sir?
Yeah. Yeah. This is a
Okay,
software
sir.
from the Desert system, Simulia.
Okay, okay, sir. So which one is best, sir? HFSS or CST, sir?
Both are similar software, but both have their own advantage. CST have their own advantage. Like in every year, in the year 2025 and 2026, is introduced some better software and better user-friendly interface also. So in previous year they introduced a VastNet, and also next year they will can introduce some um, Python scripting, advanced Python scripting. You can use in different scripting to analyze the models. Also go for the array task, advanced array task as well. So every year they get a better update with a better meshing solution and a better capability of GPU as well. So CPU or CST is good for the some complex tasks as well, because we generally before 2 days we have a session at the ISRO at Ahmedabad. So they are working on this type of antennas, in array antennas particularly. So most of the research institute are using CST for the antenna and the waveguide things, coupler things, TWT mostly. But you can analyze the all the things.
Okay, sir. Thank you, sir. Please show the help menu, sir. How to access, if
Okay.
possible.
I show with the result with as well. I get the result once. Once. So there is a part fit. I think first file is simulation is not done, so Excel ratio are not there. So I just simply see share the Excel ratio file. But here I can show the far field radiation pattern. Here you can see the 3D radiation pattern and the 1D if you have the polarization as well. Here is the radiation pattern far field for the cut. Also you can see the directivity and the orthogonal croplons are there in the linear direction. Here you can see. Plot properties are there. Here you can just change the theta and the phi value. in 1D polar. If you change the theta, you can constant the phi, and change the phi, you can constant the theta. Apply the values and you, apply. Click on OK. You can see the 1D graph of the that E plane and H plane as well. Also, you can see the directivity E field and I field are there. Also, okay, for the selectivity E theta and E phi for the 90-degree, you can see the cross planar and coplanar as well. Here you can see, one second. For the theta constant and the phi constant, you can change the gain and the E field and R field patterns. Also, you can see the far field curves as well. So, if you want to insert anything like theta and phi constant, and after that you want to analyze some result in far field result, E plane or H plane and the cross polarization, co-polarization, you can just apply the values as per your requirement, and after that you can see the result as well. You just click on apply, and file is not 90. You can just apply and the click on OK after theta and phi selecting. Firstly, I just have to insert for the theta 0. Here or and also properties there you can change. I think my CST is not fine. For the 1D polar graph, you can just simply change the values on theta and phi and get the results. And also E field and H field are with here. Here you can see the in CST. For the this is a feeding network waveguide port for the how we can analyze the electric field generate and the magnetic field generate. Here is the node prototype is so big, so you can see the small one how electric field will generate it, and how it will be changed within the time. You can see also analyzing. Also you can see the S parameters as well, in which direction it will be resonating, and also you can see in S parameter there is a also can analyze the Smith chart as well. Also you can see the VSWR value as well for the particularly resonant frequency, and some other result are there. There is a for the post processing step. So post processing step are there. You can just say go to post processing simulation and result template. 2D 3D result are there. You guys for result you can just calculate the your requirement values and apply the some requirements. After that you can analyze the some post processing step are there as already discussed. Also you can analyze the Q factor analysis, and different analysis also are there, but with the CST also, as I just explained, you can get antenna megas there with the 350 antennas. So you can directly generate it and export to CST. You can directly use it and change that dimension. Also, there is a filter 360 use the for the different type of filters to synthesize. You can directly just give the values, and you can update it to synthesize with the user of the CST. So here you can high pass, low pass filters, and the different type of filters are there. We don't go with that one, but I think you have get a particular idea about how the antenna things and some antenna array things. and optimization option are there in simulation. So optimization are there. You can select the any of this. For example, I want to change the page diameter, and there is a range from 5 to 6. Also I can increase, though if I want to increase the 10, so that will be value will be changed to 5 to 10 and give me the result. Also I can set the goal function that I want. Here I have to search. You can set the goal function as well. Also, you can for the excitation, Gaussian excitation, or any other excitation, you can also excitation uh, for the your waveguide port and the input analysis into parts. So I think that's all. If you have any query, particular query, you can ask, and or you can simply mail on this email address. So I will reply back in detailed workflow. So thank you.
Circular polarization, sir, axial ratio.
Actual ratio is actually that for the first file that analysis is not done. So I will share after the simulation done. I will share that thing. Here is the simulation is not done. So I think all results are not calculated. So I will be share in your email. Just email me in on this email address. So I will share the detailed workflow of that actual ratio and some other things for that asking in the comment section as well. Vector modeling and some reconfigurable antenna diode things are there. So I will share. Please mail on this number because it takes time to simulate the all the things. That's why. Any other queries? It's okay.
Thank you. Thank you, sir, for spending your valuable time.
Okay.
Thank you.
Thank you.